Yeah. Oh, there. Okay, let's get started. Welcome to HAO Colloquium. Today we're very happy to have Dr. Cooper Downs from PSI, Predictive Science Inc. And Cooper got his PhD in astronomy from University of Hawaii in 2011, working with Ilya Rusev. And then he went back to California and joined PSI as a research scientist and has been there since. His research focuses on understanding the thermodynamic and magnetic processes in the solar corona. He's particularly interested in the improvement and validation of numerical models through direct comparisons to observation data, and has used this approach to contribute toward understanding of various processes in the solar corona, including EUV waves, corona heating, sun grazing comets, and corona dimming. And today he's going to discuss the solar eruption signatures in lower corona.
All right. So thank you, Hanli, for that introduction, and thank you for inviting me here to speak to you guys today. And thanks to everyone in the audience for taking time out of your day to come see this talk. And yeah, I would like to thank my collaborators at Predictive Science, Tibor Dorak, Slava Titov, Zoran Mikic, and John Linker, who are all have helped me a lot with my various projects there. So I won't talk about everything I've done, but this particular talk here, the general approach for this is what I call, maybe in quotes, a realistic global coronal modeling. And this is, I say this in the sense that, well, the true 3D corona, the corona that we observe, is really quite complicated. The magnetic field is very structured. And so analytic theories or physical interpretations that we can develop, say cartoons, these can be actually very difficult to test for the myriad of solar conditions that we actually observe on a day-to-day basis. And so I would argue that numerical models, while not the be-all, end-all of science, can really serve as a sort of digital laboratory to test out ideas. So realistic simulations, in a sense, can help bridge the gap between theory and observations. And now I know Sarah is passionate about this. Forward modeling observables from numerical models is a really key element in this process because it allows you to take your model results and compare them directly and contextually to observations. So now as a quick background to the solar corona, this will be short. But basically, the solar corona, the regime that I have my bread and butter for studying, is the outermost atmosphere of the sun. What's unique about the corona is that it's very hot, but also very rarefied. So the plasma in the solar corona is dominated strongly by the magnetic field. And also the corona is sort of the interface between the surface of the sun and then the extended atmosphere of the sun that permeates the interplanetary medium, or basically it is the source of the solar wind. So it's a very interesting region to study on the sun. And what I'm most familiar with in terms of observing the corona is observing the corona directly in the extreme ultraviolet. And so from space, we can image the corona directly through optically thin EUV emission lines. And what I'm showing here are various pictures from the SDO AIA instrument on the Solar Dynamics Observatory. And for example, here, this is a picture in 171 angstroms, which is a cool coronal line. You can use other coronal lines to look at the sun at different temperatures. And the basic point I'm trying to say here is that it's highly non-uniform, both spatially, but also thermodynamically. So we see different features depending on what temperature line we look at. The solar corona is also, of course, the source region for solar eruptions, or so-called coronal mass ejections. And these are ubiquitous explosive events that originate in the corona and are of a magnetic origin. And CMEs are important for a variety of purposes, but their main function is to disrupt the ambient conditions in the interplanetary space. CMEs can be a source of energetic particles. Once the CME reaches Earth, it can interact with Earth's magnetic field. And of course, coronal mass ejections are inherently tied to the sun's magnetic field and the dynamo. But where I study CMEs is typically in the low corona. And so what I'm showing here is the low coronal signature of CMEs. So basically, as magnetic flux is ejected during a coronal mass ejection, we observe transient evolution in coronal emission lines. And so that's what I'm showing here in this nice movie. Actually, what I study most happens right at the start, but it was a fantastic movie. This active region right here flux rises, there's this big expanding bubble, and then we see a lot of material is spit out, and some falls back to the sun. And the most important thing to recognize, I think this video will go once again, is the corona is highly structured by the magnetic field. And we can see as this coronal mass ejection proceeds, there's a big bubble, this stuff is falling back. It's highly influenced by the ambient magnetic field in the corona. And so studying a CME's interaction with the ambient corona is quite interesting and quite complex. And so usually these signatures can be broken down into specific topics or subfields. And I'll talk about 2 of those today. So the first topic that I'll get into is one I've been very passionate about ever since I started studying the sun, is that of EUV waves. And especially with the launch of the Solar Dynamics Observatory, we've returned a lot of very interesting observations of EUV waves. This is a nice characteristic one, that I'll show here. There's an eruption that proceeds right over here, and we see a large-scale propagating front that reaches large transverse distances across the solar surface, or at least in the corona. And here is an example of that. The previous event I showed you, there was a bubble launched by the CME, and that, at least according in this paper, that decoupled from the coronal mass ejection itself and continued to propagate. Other various observations of EUV waves in the SDO era include apparent reflection and transmission of EUV waves, also apparent generation of small-scale wave trains traveling behind the main EUV wave front. And I'd refer you to this paper by Wei Liu et al. In 2012, where it has sort of a nice modern cartoon of all the various effects associated with low coronal CME and EUV wave. But then going back a bit in history, the EUV waves were first observed in the corona in the SOHO era, but they were predicted actually before that. And the first interpretation, or perhaps the simplest interpretation, is that the EUV wave is indeed a fast mode magnetosonic wave. And a fast mode wave is basically the magnetic analog of a sound wave in a plasma. And it's governed strongly by the conditions of that plasma, in particular the magnetic field strength. The fast mode wave is the only form of magnetic wave that can travel across field lines efficiently, at least for these large distances that we're talking about in the corona. And also important is that the expected fast mode speed in the quiet corona, at least according to models, should typically be around the 200 to 600 kilometer a second range, which is characteristic of a lot of EUV wave observations. But particularly before SDO, there were alternative models proposed to explain what we saw, because we're basically seeing evolution in coronal emission lines, and we want to know what's going on. P.F. Chen had a nice model and simulation, and here's this cartoon from that paper, where he argued that instead of seeing a wave, we're actually seeing the direct imprint of the corona as it's expanding not of the corona, of the CME as it's expanding in the corona. Also, Gemma Attrell in 2007 had a nice cartoon picture where she argued that the EUV wave front that we see low in the corona is not really a wave at all, but is in fact a successive reconnection front of this expanding magnetic flux interacting with small-scale flux at the base of the corona. And there's also another popular model called the expanding current shell model, which basically is another way of appreciating that as a CME expands in the corona, there should be some observational imprint of the edges of this magnetic flux system. And this is a cartoon from Carl Schreiber's paper when SDO was launched. Now, simulations have been a bit conflicting about the interpretation of EUV waves. So, for example, P.F. Chen said that the EUV wave was not indeed a wave at all. There was some coronal Morton wave ahead of that, but then what we observe in EUV was not truly a wave. And as time has progressed, we've had more sophisticated simulations of EUV waves. There was a nice paper in 2009 of a 2-dimensional model, or a 2.5-dimensional model of a coronal mass ejection, where that wave was modeled nicely. And then sort of going forward, some authors have attempted to model this in full 3D for realistic coronal magnetic fields and say something about the wave. And part of my past efforts was adding sort of thermodynamics into the MHD calculation. And I'll show you sort of building upon this going forward. And so then the second topic I'd like to talk about that is also intimately related to a coronal mass ejection low in the corona is the topic of coronal dimmings. And see, these are transient darkenings of nearby coronal plasma that's related to a coronal mass ejection. And so I'll show I think this is one of the SDO First Light movies that showed a really nice dimming feature. So there's a coronal mass ejection that happens from this region. And this is a few hours, I believe, where we see these deep, dark regions forming in these optically thin emission lines that is typically indicative of coronal dimming. And so the basic idea here is that this dimming or evacuation of plasma indicates magnetic field becoming stretched or open temporarily and may be associated with the erupting magnetic structure. Dimming comes in various forms. For example, this was a really nice dimming event in May 1997 that was very symmetric. So we had a bipolar active region that erupted, and there were twin dimming regions on either side. This was a very nice event studied by Larissa in 2013, where there was a very strong magnetic field and some dispersed magnetic field on the other side of the neutral line. And the dimming region was very one-sided. So you really only saw coronal dimming on one side after the coronal mass ejection. And then some authors have argued that you can really see coronal dimming signatures at large distances away from the CME site. And they've argued that that indicates some sort of magnetic reconnection process. So in a nutshell, all models of dimming invoke the erupting magnetic structure perturbing or removing coronal material through expansion or flows. But the key difference is in the physical interpretation, and this is a nice review by Pascal Demoulin, where in some models, reconnection may play a central role, in some models they won't. So for example, what I'm showing on the left is an ideal model for coronal dimming. You have a magnetic flux tube or flux rope expanding, and as it does so, just adiabatically, we'll see a reduction in density and a reduction in emission. But at the same time, you could also have reconnection play a role where you're sort of shifting the footprint of the erupting magnetic cloud, and that can cause where or when a dimming region will appear. You can also extend this model to involve successive reconnections at large-scale distances, provided that this erupting magnetic flux will sweep across these surfaces. So just to tie it all together, I sort of see this as a general problem statement if I want to study these numerically. So for both EUV waves and coronal dimmings, we see changes in optically thin iron emission. These are our observations. And we use these changes that we see to make inferences on what the physical parameters are, and that's basically the theory. And I really like this very complex cartoon that Carl drew for his paper. But I would argue that it's crucial to connect our cartoons to observations as best we can, and that's where really the modeling component comes in. So to put it in one way, this is what we might see, but really what we would like to know is what's going on with the magnetic field, the temperature, density, and the magnetic field. So the rest of this talk will then be about a case study that I've done recently about a particular event that had both good EUV wave and dimming signatures. And so I know this isn't during the SDO era, but this was during solar minimum. So I chose this February 13th, 2009 event. And during solar minimum, the corona can be much simpler than it is during an active time. And for example, at this time period, this is a stereo B observation on the left and stereo A on the right. We see only one active region on the sun at this time. And it's this active region that erupts and interacts, or the wave at least propagates across a large portion of the quiet sun. And so from a modeling perspective, this is basically as simple as you can get while doing a realistic case study. And I'll show a nice movie of this in the 171. There's a rise and then a CME. It happens quickly. But basically, this whole region right here becomes depleted. And then similarly, this region right here rises and becomes depleted as well. So there's a coronal mass ejection event perturbing the corona. This event had a nice wave signature, although the cadence isn't optimal. What we see is as the coronal mass ejection happens, we see a large wave launched across much of the corona. We see it propagating at large heights or large distances along the limb and also on the solar disk here. And so this is sort of a prototypical observation of an EUV wave. And it was for this reason that it was sort of like the simplest scenario for an EUV wave that a number of people decided to study it. So from an observational perspective, in this paper, I like their conclusion. Patsarekos and Verluidis, they basically said, well, the debate is over. This is a fast mode wave. We can show this observationally. But then in the simulation by Ofer Cohen with Gemma Attrell, they argue that it appears that both wave and non-wave models are required. And they did this with a polytropic MHD simulation and looked for how the magnetic field was reconfiguring and argued that some reconnection was involved to explain the signature. Another study that involved a large statistical sample of EUV waves found that this particular one was well consistent with a linear fast mode wave, but it was part of a larger sample. And then from a coronal dimming perspective, this particular event was really interesting. Described in this paper by McLenich et al., they studied the twin coronal dimmings that appeared during this event. And this is a figure from their paper that schematically shows the time evolution of the event. So going from purple to red, they found that the centroid of the dimming region seemed to migrate northward this way, or northeastward, and then southwestward this way. And so there was sort of asymmetric motion of the dimming regions. And they drew a very nice cartoon, one that I was interested in testing, where they argued that pre-existing shear above the erupting site, so this is what erupted, this is arcade loops above it, as this eruption proceeds, it's interacting with these sheared magnetic arcade, and then that will translate into a stretching or even reconnection that causes the migration of this dimming signature shown by these arrows. And so this is really an ideal event to study from a numerical modeling perspective because there's good observational context and cartoons for what happened. And now jumping into the model that we used, there are a couple like it now. The particular model that we used was developed by my group at Predictive Science, MAS or MAS. It's a 3D thermodynamic MHD model of the full solar corona in spherical coordinates. And sort of the hallmark of models, and especially modern models of the corona now, is adding additional terms to the ideal MHD equation to make it a thermodynamic MHD equation. This is the electron heat conduction term. You have a term for optically thin radiative losses, which is appropriate for the corona at least. And then a coronal heating term that can be specified empirically or through some sort of other mechanism for coronal heating. And it's through this term that you are really allowed to build a realistic thermodynamic stratification of the plasma in your low corona. So the steps for computing this type of model is basically, the most important thing is picking up a full sun map of the magnetic field in the photosphere or extrapolated to the corona, where basically this is your magnetic boundary condition. And this can be using observations at any time, in its essence, to model the corona at a specific time. Once we have the boundary conditions and a heating model, we can throw this whole thing on a supercomputer. Flow speed, a magnetic field everywhere that you can do things with. So you can look at the solar wind solution, or what's more interesting to me is actually generate synthetic observables from the model. For this particular event, just a detail or two about the boundary conditions we use. We took the Lockheed flux evolution model output right up to when this event occurred. This is the same model that supplies the PFSS package in SolarSoft, but we processed it a bit differently. We basically took the raw output. We spliced that with a slightly higher resolution daily observations by the Gong network. At this time, MDI wasn't quite functioning properly. The data quality was poor. And then once we combine these two maps, we can build a very non-uniform mesh for modeling the event and produce our final boundary condition, which is what I show here. So the active region that erupted was right here. This is the backside of the sun. So we have very smooth, coarse cells over here, and then very high resolution going further and further close to the active region. And then this is a snapshot of our mesh right here over the active region that actually erupted. And if I didn't mention it before, what's colored here is the radial magnetic field. So once we have that and we throw it on the supercomputer, the first step is building a relaxation for the corona. And we can start with an ideal initial condition. It really doesn't matter that much. What sets the structure is your magnetic boundary condition and your coronal heating model. And then we let the model relax for a few days, and that's what I show in this movie here. And that always starts a little slow, so I'll do it one more time. But basically, after a certain point, it's not evolving very much, and now we have a very structured structured corona because of the boundary conditions that we used. So what you see is a general correspondence between the two. We have polar coronal holes. We have closed field streamers, a quiet sun that is structured but still roughly uniform at large scales, an active region in the center that's bright. You see the appearance of this large coronal hole here and a few here. The appearance of that typically will have to do with how you process your magnetic map. Unfortunately, the polar fields aren't well observed, and that can influence where coronal holes appear. So I sort of didn't want to mess with it anymore, and this was my final solution. But going from this relaxation, there's still more that you can do. So here I show a zoom in. This is the observations in 195 of the active region, and this is the forward model observations from the simulation. So despite us opening the global field in our MHD relaxation, the active region itself is still nearly potential. And so it doesn't really resemble the observations that much yet. And in fact, this active region is roughly potential, basically because we haven't energized it yet. And so prior to now, a thermodynamic MHD simulation like this of eruptions in the global corona would have basically stopped here and then inserted an unstable flux rope basically out of nowhere that would erupt immediately, or used overly strong boundary flows that would sort of add energy and then disrupt the coronal arcade, and that's what I did in two of my earlier papers. But the problem is if you use an unstable flux rope inserted out of nowhere, that can make it very difficult to study the driver of the EUV wave, for example, or in detail the reconnection processes that occur. What you'd really like is to have a stable configuration that you sort of destabilize quasi-statically. And so in an effort to do that, we start with the flux rope model, but then do a couple things to it to build a stable configuration. And so the first model that we start with, this is the Titov demo in 1999 model, which models a flux rope as a very simple toroidal geometry with an axial current along the torus. This axial current will produce a hoop force, and this hoop force, this outward hoop force, can be balanced by the presence of a strapping field, which was in this model was modeled by magnetic charges. But Slava Titov in his 2014 paper sort of produced a slightly different formulation of this rope. Important for us, it was in a vector potential form. But in this paper, they talk about how you can take some observations or some ideal active region, calculate the strapping field that this active region would produce from a potential field model, and then tailor your flux rope parameters to use the pre-existing strapping field as the containment for the outward hoop force. And so basically you cross out the strapping field right there. And so the way this works operationally, like I said, is you can take an arbitrary magnetic field observation or an active region distribution and use its external field as a strapping field for this idealized flux rope model. You don't have to do this in your full production MHD model. You can do this in 0 beta. You can experiment with inserting a flux rope, varying the parameters and seeing what works. And eventually you can find a flux rope whose parameters are stable and somewhat resemble the observations. And so what I'm showing here in this plot is the radiomagnetic field with the footpoints of the flux rope that I inserted. And also this is the neutral line right here that it spans. And so in this plot right here, this is the initial insertion of the flux rope. Across this plane here, I show J over B, so it's this nice idealized model. But then if you insert it with the right parameters, it'll basically be perturbed slightly from this analytic formulation and adjust to the presence of the complicated field that's truly there in the active region. And so basically now we see this nice sigmoidal shape, and we have a stable flux rope that we've energized, or basically we've energized the active region in this way. And the nice thing is you don't have to use just one. You can use multiple versions. 5, 7 is what Tibor used in his latest model of a different event. But I also use this flux rope to energize the large-scale field. So this is basically one tool for building a nonlinear force-free field that then we drive to eruption. And that's what I'm showing here in these pictures. I sort of did this in 2 stages. I used a large-scale weak flux rope to energize the outer field, and then I used a small-scale strong flux rope to energize the core magnetic field that erupts. And so the first step is this is the roughly relaxed and nearly potential configuration. And here is once I've energized the outer part of the field. And by adding shear to the outer part of the field, I've sort of changed this angle to be more consistent with observations, where here it's more vertical. And then the next step is inserting a core flux rope, and I think I have a movie of this, where you can sort of see there's an initial perturbation, but this thing doesn't erupt. And then it adapts to reflect the magnetic fields present. And now we see, although it's not quantitatively exact, we see a nice qualitative correspondence between the bright emission and the sigmoidal feature in the flux rope here and what we saw in the observations. And it also has the large-scale shear of the active region. So now we have a stable configuration, but really we want this whole thing to erupt because we're studying CMEs. And so this was another neat little trick that we developed for this case study, where you want to determine some sort of boundary evolution that can drive your stable configuration quasi-statically to erupt. And in this particular case, we evolved the normal component of the magnetic field or the radiomagnetic field by driving it with electric fields at the boundary. And that's sort of represented by this equation where we decompose a tangential electric field into 2 potential or solenoidal and potential component. You can solve a Poisson equation for the solenoidal part and use various tricks for the other potential to sort of limit the range of your tangential electric field. And I show this schematically here where once I've inserted a flux rope, I've inserted it with its own flux distribution at the boundary. And then this is the original magnetogram, or basically the flux distribution I would like to arrive at after my quasi-static evolution. And that gives us a delta BR that basically this is the flux rope field that I inserted. And so by solving these equations, I can get an electric field that over a certain amount of time will transition from this state to this state roughly self-consistently. And in doing so, along the way, by inserting this energized configuration, we're almost guaranteed that an eruption will occur at some point along this stage. And that's what I show here. So there's sort of two stages. The first is the quasi-static evolution, which I show here. So I start the electric field driving, but this whole thing has not been destabilized yet. So basically, the system is rising. It's gaining relative magnetic energy relative to the potential field at any one of these flux distributions. And then there's a second phase when this thing finally no longer has an equilibrium configuration, and it will erupt. And that's what I'm showing here. So it's risen a bit, and now the eruption happens, and magnetic flux is launched and ejected from the corona. We see these sort of post-flare arcade forming here, also dimming regions as well. And so I'll study both of these in a second. So now I have this nice sort of holistic simulation of a CME in my model, and I'd like to learn something from it. And so the first application is to EUV Waves. And so in studying something like this, you can ask, well, does the simulation look like observations at all? That's sort of an important first metric. And so what I'm showing you here is sort of a qualitative view of the forward model observations. On the inside, below 1.3 RS, is forward modeled 193 emission. And on the outside is forward modeled white light emission for the limb view of the event with a radial filter that allows us to see structures far away. And we see this bubble forming. Mass is ejected outwards. We also see a large-scale perturbation of this streamer. I think this should repeat one more time. This wave is launched here, and it sort of impinges on the streamer here. But we also see what looks like a classical CME ejecta coming off in white light. Looking in detail about what happens for the wave, we can plot things in running difference. I think on the top I show stereo A, which is the limb view, and on the bottom the disk view. This is a cooler temperature line, UVI 171. This is a classic EUV wave bandpass. And then because we're forward modeling, we can also look in other arbitrary configuration or arbitrary filters and ask what would we have saw. And this is an X-ray filter from XRT. And so we see the bubble here. This will repeat a couple times too. But essentially, we see this large-scale wave propagating laterally away from the eruption site. We also see it down on the disk here. Interestingly, we also see what looks like a reflection signature right about here. And it looks slightly different depending on which filter you look at. Also, low down, we see this nice dark feature here that's sort of propagating behind the main front. And this, at least to me, as someone who studied EUV waves, does look qualitatively like one. But you can ask, well, how does this wave compare specifically to this event? And that's what I'm showing here. This is the stereo B view, the simulation and observations at the same times, or basically I've matched the model up to the observed times. And then this is the stereo A observations. And these arrows are all the same. And I'm most interested in the evolution in the northwest direction. And so at least kinematically, the outer wavefront, or this bright part, does match up with the observations fairly well. One thing you notice is that the perturbation that I've introduced in my MHD model is a bit larger than what was truly observed. And also, the event that I did is a bit more symmetric in terms of the wave. So I see it equally on both sides, while it was more asymmetric in the true observations. And this has a bit to do with the asymmetry of the actual eruption. So it's not perfect. It could be improved. But another thing, I wanted to take this a bit further, and I was fortunate to be in a group with Alexander Wormuth, who has studied a lot of EUV waves. And I had him sort of take my model data and treat it as if it were observations at this time. And he had studied, this is a figure from his paper, he had studied this event, and he applied the same technique to my forward model data. And what was kind of nice is that the kinematics were fairly close. So I think the simulation was 215 kilometers a second, according to his metric, versus 230 in the true observations. And their acceleration profile was also similar, although mine maybe decelerated slightly less. So I was happy with that. So basically asking the question, does the simulation look like observations? Yes. There's a clear wave and CME signature. The wave does propagate at large transverse distances, and the kinematics are quite consistent, at least in the northwest direction. But now that we have this, well, we can ask, well, what is the mechanism at play? So what's the underlying physics that caused us to get this observed evolution? And so for that, now we can take our model and look at the physical quantities as they go. And so what I show in this 4-panel movie here, this is the flow speed. So we'll basically see the bulk motion of the plasma. Here is the temperature, and you'll see a cavity forming. This is the divergence of the velocity, and I found this to be a nice parameter for diagnosing compressive waves in the corona, or in an MHD simulation, rather. And over here I show in the plane of the sky J over B, which is useful for sort of highlighting where currents are present or boundaries between magnetic flux systems. And so as this proceeds, we see large velocities form, and then plasma is ejected outwards. That's typical of a CME. In temperature, should have repeated. In temperature, we see a low temperature sort of cavity forming, and that's following the CME ejecta as well. In divergence of velocity, we see sort of a nice sharp wavefront forming that looks sort of like a bubble, and we see that this trip propagates at large distances away from the eruption site. And we can sort of distinguish between that and the CME, between wave and CME-like features by looking at J over B, where here this is really the erupting magnetic flux system, and then we see that wave is sort of decoupled at the flanks. And I can prove this a bit better by looking at the magnetic field line evolution, which is what I show in this movie here. So now I've traced magnetic field lines that represent open in magenta. The streamer above the active region is here in blue. Other streamers in low-lying field as well. And then right here, these gold field lines are the erupting magnetic flux rope. And I've superimposed on top of this the divergence of the velocity, or the negative divergence of the velocity, which indicates the outer front of the wave. And so this flux rope expands and then erupts. We see that this wave decouples strongly from the erupting magnetic flux system. So this wave is free to propagate through these open field regions and interact with the streamers, but the CME does not reach those distances. And then we see the erupting magnetic flux goes outward this way, but also does not have that much lateral expansion in this direction, particularly low down in the corona, where basically all the field lines are still rooted relatively close to the active region. And then this is just another rehash of that, comparing it to what the forward model observations look like. I'll just show this once, where we see this ejecta here roughly corresponds with the gold field lines, but then this wave here corresponded with the div V front.
Question.
Uh-huh.
So when the wave is interacting with the streamer, it looks like it's almost not interacting. Those are in the same plane. If it's a fast mode wave, I would expect compression.
Yeah, actually, it is interacting. You see this right here. You see this sort of.
I see it up at the top,
angle,
but not,
yeah.
so not down low because the field's stronger?
Exactly.
Okay.
Yeah. So there's not enough energy content in the wave to really have a strong perturbation there, so you don't see it as much. But it does pass through. And if you were to sort of plot a smaller perturbation, you would see it further down. Mm-hmm. So basically, my conclusion from that is we can use the simulation to look at the underlying variables. And so my strong opinion from analyzing the simulation is that, well, at least for this case, the outer front is very consistent with the fast mode wave because that's what we have in the model, and that lines up with the wave. The wave also is driven by CME expansion, so this gets us at the driver of the wave low in the corona. Basically, the wave decouples from the flanks when the expansion of this erupting magnetic flux system stops. And so that was the wave application. And then just a few more slides here on the application to coronal dimming. Similarly, now that we have the CME eruption, we can ask, well, what is the dimming signature? And so that's what I'm showing now in a zoomed-in view of the forward modeled observations. Actually, I'll go back. In the forward model XRT observations, we see this sort of nice, very bright structure that outlines the presence of the flux rope. And so that kind of looks like a sigmoidal feature you might see in a decaying bipolar active region. So now this whole thing is rising. Reconnection sets in. We have this post-flare arcade forming, and we also have dimming regions that form on the left and right. Also, if we look on the limb view, we see that this bright emission here is basically fully depleted by the eruption. And so again, looking at the disk signature, I just sort of did this quickly. where the red highlights where the regions of strong emission depletion as a function of time. So this is before the eruption and as it proceeds. And we see the formation of core dimming regions and then sort of the subsequent evolution of these regions as well. And so this is what I'd like to study. And basically what I'd like to understand is what's physically going on. And so what you can then do is look at how the magnetic field is evolving. And this is a bit quick, but one of the primary tools that I think is very useful for this type of analysis is that of field line mappings, and in particular this variable or this factor called the generalized squashing factor described by Slava Titov. Basically, you can map a lot of field lines from one boundary to another and then calculate how does this mapping or an infinitesimal flux tube deform as it goes from one boundary to another. And this is basically related to derivatives of the field line mapping. And this can be an extremely useful diagnostic for mapping interesting regions of the magnetic field because this Q factor becomes infinite in the presence of a true discontinuity or a magnetic separator. And this Q factor becomes very large at quasi-separatrix layers. And those are thought to be very interesting in a topological and coronal mass ejection sense. So what I'm showing here is on the left is the log of the generalized squashing factor Q. Black indicates high Q and white indicates low Q. And what I've done is I've taken field lines that I had vec'd throughout the simulation at the apex of the flux rope, and I'm showing their mapping back to the boundary at r equals 1. And so this is typical of sort of a sigmoidal energized active region or a flux rope, where you'll see this S-shaped high Q line. And then as I apply electric fields and the thing begins to rise, we'll see evolution in the high Q lines. And then when the eruption proceeds, we'll see significant evolution in this generalized squashing factor. And that's what we see here. So there are a couple interesting things to point out. I hope that this thing will repeat. Is basically as the flux rope erupts, I'm advecting my seed points along through the domain. And so they always map back down to somewhere in the solar surface. And where these field lines map back down is always in this high Q sort of closed contour here. There's structure inside that indicates internal reconnection dynamics. But basically, the footprint of the magnetic cloud always follows this generalized squashing factor contour, which migrates across the solar surface. And so this can be used as a nice proxy for where the footprint of the magnetic cloud is going. And so taking this as a proxy, I can now overlay it on top of my forward modeled EUV emission observations and see how that evolves. So that's what I see in this red color over the blue, over the green. And so we have core dimming form, and then migration of the dimming region. This flare arcade is expanding, and we see that the footprint of the magnetic cloud is roughly correlated with the footprint of the dimming region, but they don't overlap one-to-one. And so this is useful. First, it tells us there's a general correspondence between at least these deep core dimming regions and the erupting magnetic cloud footprint. But it also tells us that you can't just use the dimming region as a proxy for the footprint because they don't match up one-to-one. So another way of putting this is, or asking is, well, why don't the dimming region and the footprint overlap exactly? And we can now look in more detail at the simulation as well. So I put this little line here, and now picture extending this plane out of the board and then rotating it 90 degrees up. So now we're looking down into the solar surface. And so I visualize the line of sight emissivity along this plane that I show here. And now I can play a movie of this where we see what happens. So this is the erupting magnetic flux system right here. It rises. Reconnection sets in. This is the post-flare loops right here. And then we see this dark tunnel that's formed right here. And that's basically the dimming region. But what's important is that if you're looking straight down, you see that there can be projection effects involved because this thing is tilted. And we can characterize this also looking at other simulation variables as well. This is J over B here, like I showed you before. I also will show the total loop length, and field lines get very long when they're part of a magnetic cloud. They'll turn orange and red as the movie proceeds. Also, I have temperature, which is hot in the active region and cooler outside, and the line of sight emissivity. So I'll play this movie maybe twice here. So this flux system is rising. We form a large-scale current sheet. Reconnection occurs. And then to the side of this, we have very, very long loops next to very, very short loops. very, very hot loops next to very cool loops. So this is basically the post-flare arcade next to the footprint of the erupting magnetic cloud. And again, we see that this low temperature region corresponds nicely with this dimming region in the emissivity. So now we can put this all together also in terms of the physical mechanism for the dimming. And this may not apply to all events, but I think it was the case for this event, as we can actually look at the magnetic interaction of how these dimming regions are formed and subsequently migrate. And I show that with sort of representative field lines for the relevant flux systems. So this red field line here, and these are all just different orientations of the view. This red field line here is a central field line that erupts with the core of the magnetic cloud. This blue field line here is initially an arcade field line that's not a part of the energized structure, but it's sort of overlapping or on top of. And then here, this orange one is another arcade field line that's close to, but not exactly where this blue field line is. And basically what happens is I'll go through this once. The red field line rises, the whole arcade is perturbed slightly, but then once reconnection sets in, we see that this blue field line now becomes part of the erupting magnetic cloud. And so what was originally an adjacent field line, part of the arcade, it's shown nicely here, this thing is not part of the erupting magnetic flux system. Basically, this leg of it gets sucked into the flare arcade, or the reconnecting current sheet right there, and now becomes part of it. And so then the other leg of this field line maps back into the dimming region that is migrating northward. So basically, this is a mechanism for taking initially surrounding magnetic field and involving it in the eruption, and then subsequently dimming the footprint of that shared arcade field. So just to summarize the results here, the formation and transverse migration of this dimming region in the simulation is qualitatively consistent with the observations. We identified the reconnection of the erupting flux rope with the surrounding shared arcade as the primary mechanism for the apparent motion of the dimming region. And what I think is interesting is the spatial location of the dimming region is well correlated with the footprint of the erupting magnetic flux system. But its spatial location does not fully overlap, or at least for this case, with the photospheric footprint of the rope. That may not be true for other events. And then ideally, we'll extend this type of modeling to more complicated dimming signatures in the future. So then just as my last slide, sort of philosophically, the approach here is constructing realistic models and forward modeling observables allows us to directly link what we see to what we think could be happening. And although it's maybe not the important aspect of scientific research, I think it is a key aspect for connecting observations to theory. And this type of coronal modeling, the type of case study that I showed you here, does have many applications because you can capture the coupled interaction of a CME flux system with the ambient corona. So we can study things like EUV waves and coronal dimming, like I just talked about now. But also, one of the interesting things that we've looked at in this simulation is the generation of quasi-periodic fast mode waves related to reconnection in the flare current sheet. I mean, in more general terms, you can use this type of simulation to study flux rope evolution in the low corona. Things like rotation and deflection of CMEs, also propagation, and then the internal and external reconnection or reconfiguration of CMEs. So basically, that's it, and thank you for listening.
Questions for Cooper? Yes. So, kind of interested into your projection effects, how that, where you see the dimming isn't necessarily the actual foot point of the magnetic field. Have you tried looking at doing these simulation the intensities you see, but for different wavelength channels, so you see maybe perhaps different heights in the atmosphere, and the different region then is not always in the same place?
Yeah, well, that would certainly be the case. So the problem with the corona or the low corona is like the scale height's not small, or at least relevant to the region that you're interested in. And you're right, if you look at different temperature lines, that may have a different scale height, and so you may be imaging a different portion of the corona. I haven't done a detailed study. I think maybe John Q has looked into this, dimming signatures in different wavelengths.
Then I wonder if you can use, if that works out, then you can use it from actual observations to diagnose the direction of what the field's doing there, just by looking at how.
Yeah, right. Yeah, it might be complicated because I think the best observed lines all still have a substantial scale height. Maybe you'll see some differences between 171 and other ones. In terms of the projection, if you really want to connect back to the photosphere, right at the bottom here, where's my pointer? This thing kind of goes to this tiny little region right here, even though you might characterize this whole width as having dimmed. So it might be kind of hard. What this did convince me of, though, is using, and this is obvious, it's not new, but using flare ribbons that you see in like a chromospheric emission line or chromospheric observations are probably really right on top of where the footprint of that arcade is, because then the scale height is very, very small.
So first of all, thank you very much. It's a very, very, very interesting work.
Oh, come on, thanks.
I know that you're kind of focused on dimmings, but I have a question about that reflection that we saw from the South Pole. It may contain some interesting physics in the model. And there was a slide where you showed a movie of a cross-sectional north to south slice of the simulation. And I couldn't easily see the dimming, the reflection on it.
So are you talking about this movie here in the physical quantities? Yeah, I think it would be most obvious down here. The problem is the wave amplitude gets sort of small, so it's a scaling effect. And it goes out of the frame. I have movies where I go further. So basically, the structure that it reflects off of is down here. You might be able to see it here. So I could show you offline a larger movie of div V. But essentially, we see some reflection behavior right here before I stop the simulation. And what this has to do with is actually right here. Basically, this wave goes nicely through this streamer pretty well. But then once it gets to here, it reflects off of this high-speed region that is in the coronal hole, and then it starts coming back.
So this is actually that very movie. If you don't mind playing it.
No. Unfortunately, I only did the negative velocity divergence, and it kind of gets obscured because I didn't choose a strong scaling. So you might see some reflection of this front right here. No, not really.
Actually, if you can pause
There's
just
that one.
right here.
Sure.
Going.
Tell me when.
Now. Okay, so there are two kind of bubbles in that southern region. One is far away, one is closer. And they move in different directions at different speeds. Can it be that what we saw, that what we perceived as reflection in the line of sight integration was just an overlap of those two features?
Yeah, I mean, we're moving large-scale structures around, and so it's not as simple as the wave reflected here, and that's what we're seeing. You're sort of seeing the cumulative effect, and you're seeing this whole streamer perturbation here. So maybe I was a bit glib in using the word reflection, but you'll see that this part is pushed right here. It goes in, and now there's a rarefaction part here. And it's that rarefaction that will probably look like the returning front in the EUV wave.
Or it can be actually the overlap of the frontier feature and then the kind of the secondary feature.
I'm not so sure about that. The problem is the emission scale height is really centered down here. So in the images I showed, you wouldn't have much sensitivity to this structure up here. There are a couple observations of streamer oscillations in white light, and you see this type of behavior, but I haven't studied it in detail.
Really nice stuff. I had a question. So in getting that flux rope and adding it to make it look really nicely like this particular event, and you mentioned you have to kind of tune the parameters and get it to work.
Mm-hmm.
It would obviously be great if there was a way to feed the observations back in to actually drive the choices of parameters in an automatic sense with observations. And so to get a sense of the reality or the realism of that at some point in the future, how long does it take? How much computational time does it take? How intensive is that parameter fitting stage of the process?
Well, that is something we're working on, not in terms of necessarily an observational feedback, but we're trying to optimize the whole step of inserting a rope and assessing whether it's stable or not. And then the final stage of that would then be comparing in some way to observations, hopefully through Kevin's help or yours.
Yeah, but the trick is to get the observation not as a final step, but as a step that drives the direction.
Yeah, I think that would be difficult because it's sort of hard to predict what's going to happen in detail. I mean, you have stable or unstable is one thing. This thing might erupt. And then also, if you really need to fit field line geometry, you're sort of inserting this idealized thing and then hoping it'll reconfigure in the right way. And that's more of a trial error process rather than I know what's going to happen.
And how long does it take to say let it relax to find out where it's going?
Well, the nice thing is we can do this in 0 beta. So as long as you believe that your active region is roughly low beta, you can get a good sense, maybe not perfect, but a pretty good sense of what will happen when you put it in your thermodynamic MHD model by running a much more simplified 0 beta model. And that you don't need as many points to resolve the full sun, for example. And the physics is much simpler. So we can run that sort of simulation on a 20-core machine rather than a 1,000-core machine in a matter of 30 minutes or something like that. And so if you were really ambitious, you could probably optimize that by a few factors as well. But it still involves a 3D MHD model. Yeah.
That's interesting.
Mm.
Have you looked at what happens to the dimming past its peak time? How the field lines move back maybe to the original, how the whole region structures towards the end of the dimming lifetime?
Unfortunately, dimmings last a long time, and I didn't want to use that much computer time. So I studied it mostly to get the formation and migration of the dimming regions. Once the corona closes back down, they kind of fill back in relatively quickly. But in terms of many hours later, what happens, I don't have a model of that yet.
I mean, like the footpoints, what happens? Do you have some thoughts on what happens to the footpoints? Do they move back to their original position, or is it just they stay where they are and just fill up with plasma and become bright?
My impression from the simulation is really you get, because if it's still associated with a magnetic cloud, that's essentially a coronal hole. And just by themselves, those are dim. And so I wouldn't expect it to come back to the quiet sun level if it was originally at a quiet sun level or part of the active region arcade. So my impression, just partially based on my physical intuition and then the simulation, is that, for example, this core dimming region gets partially obscured by the flare arcade, but also the reconnection is continuing in my simulation, and the footprint is moving. And once it's moved substantially, then this is sort of filling back in. So I'd expect that at least if it's a core dimming signature and it really is part of the magnetic cloud, it would stay dim for a long time until the corona finally closes back down.
Right, but let's say that within a day, the region goes back to its initial configuration. So pretty much it goes back to how it was before. In this scenario, your footpoints would be permanently in their new position instead of returning where they were.
Right, well, they are continuing to evolve. And so at some point, I'm a little less clear on this because this isn't really what I set out to study, but the footprint of the magnetic cloud starts evolving towards where an original coronal hole was. And so it might be at some point through the subsequent evolution of these footprints, you no longer are seeing the dimming region anymore. Right.
Particularly in this case, because it would be joining
the pre-existing coronal hole. And so you would say the region's back to normal, when really there may be some field lines part of the magnetic cloud out in space connecting back down. They've just moved, essentially. Cool, great, thank you. Oh, thanks. Cheers. Okay, good. I was worried about that.